Now, as I mentioned, there are two ways of viewing AdaBoost. The first one is, as we talked about, it's a method that reweights the data and calls the weak learning algorithm over and over again to produce weak classifiers. Fine. The second way is that it's coordinate descent on the exponential loss. Okay, so how do we reconcile these two views? I mean, what space are we working in for coordinate descent? Well, let's think about what coordinate descent is. It's a method that minimizes a function by moving along one coordinate at a time. Okay, so you start out and you minimize the function by moving along that coordinate, and then pick another coordinate and you minimize, and so on and so forth until the function's minimized. Good. Okay, so what space are we working in then? Well, let's say that we are running a decision tree method as the weak learning algorithm. So at every iteration, you call, the weak learning algorithm is called and it's producing a decision tree. So this is like, C4.5 or CART, right? So the set of weak classifiers you're thinking about is the set of all possible decision trees that can be produced by CART and C4.5. So this is an enormous space, right? And so I want you to think about each direction in that space as corresponding to a different decision tree. Okay, and the decision trees are the weak classifiers. And then what does it mean to walk along a direction in this space? Well, what it means is that you're adjusting the coefficient on a tree. Okay, so at every iteration, the weak learning algorithm picks a tree, and then AdaBoost adjusts its coefficient. Okay, so it's moving along this space to try to minimize the exponential loss over weighted combinations of these trees. Cool. So I have all this terminology fused in my head because I think about AdaBoost as a coordinate descent method. I did my PhD on this topic, so I think about these things together in the same way. So when I say weak classifier J, I mean coordinate J in this space of weak classifiers. And then when I say run the weak learning algorithm, I mean choose a weak classifier. And if I'm choosing a weak classifier, that's a coordinate in this space. And then when I say I'm moving along direction J by a distance alpha, I mean adding alpha to the coefficient of weak classifier J. Okay, so that's our way that we can view this. And so when we're updating coefficient J by alpha, that means that we're adding alpha to the coefficient, that Jth coefficient for the final combined classifier. Okay, so I should mention that I overload notation where index T means iteration number, and then index J means, okay, if I wrote all the decision trees out, it's decision tree J, right? So I can write the final combined classifier, I can write it as a sum over J and then add up all the updates that we had for each weak classifier J. But another way to write it is you can just write it as, the sum over all iterations, and then you add up the updates to the coefficients that you made for each weak classifier. Okay? Cool. Yeah, so alpha t is the update to the coefficient of weak classifier that you got at iteration t. Cool. Okay, so how are we then doing coordinate descent? Well, until we're converged, we're supposed to choose J, which in this case means run the weak learning algorithm. And then we optimize the function along direction J by choosing a coefficient alpha to minimize the objective, okay? So we're gonna actually derive the expression for alpha as, a line search in that direction, kind of in the next video. Now I should mention that the weight vector D, which was a discrete distribution over the data points, that actually doesn't have a meaning in the coordinate descent view. You can think about it kind of as a dual variable, or as a variable that's kind of handy for transitioning between one iteration to the next iteration and telling you kind of, okay, how should I reweight the data so that I can pick out the best direction to go in the coordinate descent view of things. But D actually, it doesn't really have that kind of a meaning. So you really want to only think about it in the other viewpoint of AdaBoost. Okay, so let's take a look again back at AdaBoost pseudocode. So you start with uniform weights over the data points. At each iteration, you train the weak learning algorithm, and this produces a weak classifier. And then that's the same thing as, of course, choosing a direction j. And then you choose a coefficient alpha. That tells you, how far did you go in direction j. And then you update the weights, which again helps you just transition to the next iteration. And then you output the final combined classifier. Okay, so this is actually the exponential loss. You've seen this before. And F is a linear combination of the weak classifiers that we've collected using all the iterations. And then I can rewrite this, instead of indexing by t, I can actually index it by j. Okay, so again, the meaning of t and j changes here, because t means the weak classifier collected at iteration t. Then hj means the jth weak classifier if I enumerated all decision trees, right? Okay, so I can rewrite this sum over t, I can rewrite it as a sum over j. And this is like, what you're doing here is for each j, you're saying, okay, how far did I go? What are all the updates I made to the coefficients for that weak classifier, right? So maybe at an early iteration, you updated an alpha, you added an alpha to that coefficient, and then later on you came back to that coefficient, added another alpha, right? So then you would add up all those alphas that you got for that weak classifier and put them all together, and you could call that thing lambda for coefficient, coefficient j for weak classifier j. Okay, cool. Yeah, t is different than j. I explained that already. Okay, so then you can write f of x as being this linear combination over all possible weak classifiers, and then lambda is the total weight that each weak classifier j gets in the final combined classifier. Now, I want to note again that AdaBoost was derived using the weak learning perspective. I don't know how Rob Shapiri, he got that formula for alpha out of his head. I have no idea how he got that thing, but he got it by changing the reweighting values until he actually got something that converged very quickly to a small exponential loss and to a low classification error. So it's amazing that he got these formulas without using the coordinate descent view, but they did. Okay, so it was only after AdaBoost was published did researchers notice that AdaBoost was coordinate descent on the exponential loss. But once you know that, it makes it very, very easy to derive AdaBoost that way. And so in the next video, I'm going to actually derive AdaBoost using that coordinate descent perspective. Thanks.